This is found in your master lecture packet that I put in the syllabus area of Blackboard. So this is the week 1, week 2 material, the chemistry of life. So we know that biology is a study of life, so we're going to talk about chemistry as it relates to living things. So matter, we said, is anything that takes up space and has a mass. So those two important pieces define matter. And all organisms then, because they take up space and have a mass, are considered matter. So when we look at what it's made up of, matter is classified in the periodic table as elements. So the periodic table of the elements are how to describe them, made up of atoms. So when I look at a carbon, the element carbon, it's representing an average carbon atom. So we'll talk about that. You have a periodic table in your textbook. I'm not sure if it's at the end of the textbook or if it's in the chapter. I'd have to, there's a little bit of a periodic table, a portion of one, on page 22 of your textbook. Figure 2.3 has a portion. And if we pull out one of those atoms, for example, carbon is the atom that defines living things. Carbon is found in every living organism. So if we look at carbon in the periodic table, it has a capital letter C, and above it is the letter 6, or is the number 6, and below it is the number 12.01. So we're going to talk about what those numbers mean to us and what they tell us about an average atom of carbon. So this is an average. So if I look at the top number, we call that the atomic number, and the bottom number, the 12.01, is the average atomic mass. It means if I have an average carbon atom that exists in the world, the average mass is 12.01. So that means some are a little heavier, right? Some are a little lighter, and we come up with 12.01 as the average atomic mass. We'll talk about and kind of review these things. I'm sure you've heard about this in your high school classes if you haven't had a science class here on campus yet. Physical science is when we usually introduce this in high school in 9th grade. So anyway, an element is a substance that cannot be broken down to other substances, so it's pure, and that's what we put in the periodic table. It's found out, maybe combined in nature with other elements, but we can't break down that element into anything smaller. And a compound is when we mix elements together. So sodium chloride, table salt that you pour on your food, that's a compound. It's sodium and chlorine, 2 atoms bonded together. And we'll talk about the different types of bonds. So when we look at these different elements, 25 are essential to life. We cannot live without these elements. And when we look at what makes up most of living matter, it's carbon, hydrogen, oxygen, and nitrogen. 96% of us is made up of those 4 elements. So a good way to and the other 2 are phosphorus and sulfur. So I'm not sure if I mentioned that before, but you can use the word chnops, CHNOPS. Those are the top 6 elements in living things. So other important ones are calcium and potassium. So when we look at percentages, we can see these top 4, oxygen, carbon, hydrogen, nitrogen. If we look at what's most abundant, it's oxygen, because we know as like human beings, for example, we rely on oxygen. We carry it on our red blood cells bound to hemoglobin. And we know that water, so that's 2 atoms of hydrogen bonded to 1 atom of oxygen, makes up most of our body weight, and mostly water. So looking at the periodic table of the elements then, it tells us about what those atoms look like. So I'm going to increase the size here. So if I look at carbon, for example, the number 6 is written above carbon in the periodic table. It tells us the number of protons and the number of electrons in an atom of carbon. And you see the yellow circles around there, around the outside? This represents energy levels where we find electrons for each of these atoms. So if carbon has an atomic number of 6, or let's look at the helium example. Helium has an atomic number of 2 and an atomic mass of 4. So an average atom of helium weighs 4 AMU, atomic mass units, if we round it to a whole number. So the top number, atomic number, tells us that helium has 2 electrons and 2 protons. So when you look at these protons and electrons, you have to know a little bit about where they're located. Where do we find protons? What? In the nucleus of atoms. All atoms have a central core called the nucleus, and that's where we find the protons. They're positively charged. And then there's these yellow circular energy levels around the nucleus where we find electrons, and they're negatively charged. So we have positively charged protons in the nucleus, negatively charged electrons in these yellow energy levels around the nucleus, and they're attracted to each other. Negative and positive charges attract each other, and this is what holds the atom together, is when we have equal numbers of electrons and protons, that holds that atom together and holds it intact. So all atoms are electrically neutral because of having the same number of electrons as protons. But when we find out the mass of helium, if I take 2 electrons and 2 protons, if they each have an atomic mass unit of about 1, that would equal 4, right? So 2 plus 2 would be 4. But what we find is that electrons have such a tiny, tiny mass, it's almost negligible. So where do we get an atomic mass of 4 from? If electrons are super, super tiny and light, where do we get the other 2 to get an atomic mass of 4? Yes? Yeah. Also, what we discovered in the nucleus are another set of atomic particles, subatomic particles called neutrons. They don't have a charge, but they hang out in the nucleus with the protons, and they contribute to that mass. So notice that these yellow energy levels, there's more than 1 or 2. The higher the number, the more energy levels we get. So what we have observed is that when we look at energy levels, the first energy level that's closest to the nucleus here, so this white is the nucleus, the first energy level can only hold 2 electrons. Then that energy level is filled. So any more electrons that might be in that atom, based on its atomic number, goes out to the subsequent energy levels. And each energy level, other than the first one, can hold up to 8 electrons. So we call those electrons that are in the outermost energy level, we call those valence electrons. So they're outer energy electrons, and those electrons are what can participate in bonding. So let's say we have, well, except for, I should say, if we have 8 electrons in the outermost energy level, that energy level is full with 8, and there's no bonding that occurs. What do we call those elements on the far right side of the periodic table? Helium, neon, yes? The noble gases. And when I think noble gases, I think, well, they're too good for everybody. They're noble, okay? They have outer energy levels. They don't participate in bonding because the energy levels are full with 8. Like we said, the first energy level can hold 2. All the other ones hold 8. So if the energy levels are full, no bonding is going to occur. So those stay by themselves. So we see helium gas as helium gas. It doesn't bond with other atoms. So when we look at bonds then, bonds with incomplete valence shells, where those outer energy levels don't have 8, they have some number less than 8, then we see those atoms either sharing electrons with other atoms, or they transfer an electron from their outer energy level to another one, or they take one in from another energy level. And when we have that sharing or that transferring of valence electrons, it forms an attraction, which we call a chemical bond. So the first example is a covalent bond, and the key word to remember is it's sharing electrons. So we're not transferring from one atom to the other, they're sharing. So they're overlapping their outer energy levels, and those electrons are hovering between both outer energy levels, and they're sharing those valence electrons. So here's an example of hydrogen. What's the atomic number of hydrogen? Do you know where it falls in the periodic table? As 1. It's periodic. It's in spot number 1 on the periodic table. It's in the upper left. So it has an atomic number of 1. So what does that tell us? How many protons does it have in the nucleus? 1. How many electrons does it have floating around in that first energy level? 1. So the atomic number always tells us the number of protons and the number of electrons, and they're always equal. So if I have 1 proton, I have 1 electron. So that 1 outer valence electron is floating around in this first energy level. What did we say is full for that first energy level? What's the max it can hold? 2. So this is not full, right? There's 1 in there. It needs how many more to be full? 1 more. It needs 1 more. So what hydrogen does is when it encounters another hydrogen atom in the environment, those 2 atoms hover near each other, and you can see their outer energy levels overlap. And to those atoms, it feels like each has 2. And when each is 2, they're stable, and they exist as hydrogen gas. So how would I write the formula for hydrogen gas as it exists out in the air? Hydrogen mostly exists as water, but if I was making hydrogen gas, what would it look like? What would be the formula? How many hydrogen atoms are there? How many are in that bond? 2. So the formula for hydrogen gas is H with a little lower 2 to the lower right of it, because there's 2 hydrogen atoms bonded. So this is covalent. When we say nonpolar, nonpolar means equal sharing of those valence electrons. So either one of the electrons is equally distant from that nucleus as the other hydrogen atom. So they're equally shared. It's a nonpolar covalent bond, equal sharing between those 2 atoms. If I look at water, for example, water is different. Water has a covalent bond, so they're still overlapping. But what we find is that hydrogen atoms, again, they need 1 more electron, right, to fill their outer energy level. But if I look at oxygen, its atomic number is 8. So it has 2 in the first energy level, and how many are in the next energy level? 6. How many more does it need to be full? 2 more. So it's going to share 1 electron with 1 hydrogen atom, but then it needs another hydrogen atom to share its electron. So it needs 2 hydrogen atoms to get 8 in this outer energy level. But what we find is that oxygen pulls those electrons a little closer to itself and further from hydrogen. So it's a selfish sharing. One is the taker in the relationship, and one is the giver, right? Just like people. So we give this little symbol here for oxygen, that little Greek letter, is that lambda? I think. With the negative sign, means it's pulling those negatively charged electrons a little closer to its nucleus compared to the hydrogen atoms that are losing those electrons, and they're being pulled away, so they're losing a little negativity of those electrons, so they're slightly positively charged. So we call this a polar covalent bond because we're still sharing electrons, but the electrons are being pulled a little closer to oxygen than hydrogen. And the formula for water is H2O, right? Because the oxygen requires 2 hydrogen atoms to fill its outer energy level with 8. So we'll pick up next time talking about the other types of bonds that we see among atoms.